All right, moving on. Question 19 on the math subject GRE practice test. Last couple videos have been kind of long. Good news, I don't think this one's going to be. But I do have some pretty useful stuff that I want to make sure you know for this problem. So what this question asks is just what is the point on this curve that's closest to the origin? I'm not sure why they did this, but of the 5 points they gave you, only 4 of them are even on this curve, right? If you plug 1/2 in for x, you get the square root of 3.5, so what, 7/2? And the square root of 7/2 is not a rational number, it's not 3/2. This point right here is not even on this curve, so I don't even know why they list it, just to mess with you, I guess. I think these other 4 points are on the curve. If I didn't know at all what I was doing, the fact that they're talking about distance, specifically distance to the origin, makes me think the answer is probably not going to be A and probably not going to be D. They're probably not going to pick a point on one of the two axes, where finding the distance becomes kind of trivial. The distance here is 3 and the distance here is root 3. Without even working the problem, I bet the answer is going to be B or C. We can certainly eliminate E, and I guess the fact that the square root of 3 is less than 3 means we can certainly eliminate A as well. Once you verify that this point is actually on this curve, which is pretty straightforward, right? Change all the x's into zeros, y is going to be root 3. So we're down to 1 and 3, suspecting it's not this one. If you want, flip a quarter and move on. But what would be better is to be able to actually solve this. Since we're looking for closest to the origin, maybe you'd think to employ the distance formula. This is definitely one you'd want to have memorized. I think I talked about it in a previous video. It's just the difference in the x coordinates squared plus the difference in the y coordinates squared, and then take the square root of that sum. The little picture that I have in mind is you got a point, I don't know, here and a point here maybe. Call this one x1, y1. Call this x2, y2. To figure out this distance in green, all you got to do is draw a right triangle. There we go, right enough. If you had to find the length of the hypotenuse here, maybe you would think a squared plus b squared is equal to c squared. In other words, c is the square root of a squared plus b squared. Here's the c, here's the a, and here's the b. Anyways, conveniently in this problem is that one of the 2 points in question is the origin. So we can change the x1 and the y1 in this formula into zeros. And that tells us that the distance is equal to the square root of x squared plus y squared. You're like, oh, still got 2 variables. Right, but one of them is defined in terms of the other one. Y is just the square root of x plus 3. Since the other point that we're looking for distance falls on this line, we can change the y of the other point into the square root of x plus 3. That tells us that the distance is equal to the square root of x squared plus the square root of x plus 3 squared. Cancel stuff out a little bit, and we get that the distance is the square root of x squared plus x plus 3. Cool. Since we want closest to the origin, you're thinking we want to minimize the distance. Whenever you see this word minimize, you're thinking first derivative. Specifically, when is the first derivative equal to 0? Where do I have critical values? So it's not d that I'm interested in, it's d prime. It's a bit of a problem with figuring out d prime. It's kind of annoying, right? Because of this square root right here. I mean, you can do it. You could bring the 1/2 down in front, and then you got x squared plus x plus 3 raised up to the negative 1/2 power, but then you're not done. Think chain rule. The derivative of x squared plus x plus 3 is 2x plus 1. And now I have this huge mess for my derivative. At this point, what I would do, since I'm trying to minimize the distance, is look for critical values. In other words, set this equal to 0 and solve. It's actually not that hard to solve. I mean, I guess I've gone this far, I'll do it. You could rewrite this as a fraction. So the 2x plus 1 is up on the top, and the 2 from the 1/2 is down on the bottom. And then this x squared plus x plus 3, since it's raised to the negative 1/2 power, it shows up down on the bottom, raised up to the positive 1/2 power. You could replace this positive 1/2 with the square root, but really you don't have to, because if you stare at this, you might realize that the only way a fraction will equal 0 is if the numerator equals 0. So solving this equation is equivalent to solving the equation 2x plus 1 equals 0. But I think a lot of people wouldn't make that connection. They'd see this ugly derivative and then set it equal to 0 and be like, that's more algebra than I want to do, which I think is totally reasonable. I got a cool trick here. Anytime you're trying to minimize the distance, you can take advantage of the fact that the minimal distance will happen at the point that also has the minimal square of distance. In other words, to minimize distance, you can just minimize distance squared, right? You're standing in a room and you're trying to figure out which person in that room is closest to you, and one's 3 meters away, and one's 5 meters, and one's 10 meters. Instead of considering all those distances and figuring out which number is the least, you could square all those distances to make them, 9 and 25 and 100, and pick the one with the lowest square of the distance. That works because distance is always positive. And you're like, yeah, but that would be a weird way to figure out who's standing closest to me. That's true, but if minimizing distance is the same as minimizing distance squared, instead of taking the derivative of the right side of this equation where distance is written as a function of x, I could take the derivative of the right side of this equation, where distance squared is written as a function of x. The advantage here is now the derivative is really nice, right? It's just 2x plus 1. Setting 2x plus 1 equal to 0 is a lot easier. Maybe if you're really paying attention, you'd be like, wait a minute, that's the exact same thing that we'd be doing over here. Right, you get to the same point, you get to the same answer. That's exactly what I'm trying to say here. It's just that your calculus is a lot easier, and even your algebra is easier. This is easier to solve than this. Anyways, one way or another, you figured out that your critical values happen when 2x plus 1 equals 0. In other words, 2x equals negative 1. In other words, x equals negative 1/2. At this point, we don't know if x equals negative 1/2 is a local minimum, a local maximum, or neither. I guess if you really wanted to, you could either do the first derivative test or the second derivative test to classify this critical value. But I think what most students do is they find this critical value and they assume it's a minimum. They look for where x equals negative 1/2, which is answer C, and they call it good. I guess technically, we could take the second derivative of this distance squared thing. The derivative of 2x plus 1 is just 2. Change all the x's in this expression into 1/2. Since there are no x's in this expression, that just evaluates to 2. Because 2 is greater than 0, we know that the function distance squared is concave up when x equals 1/2. It's actually concave up everywhere. The fact that it's concave up means it kind of has this shape. At the critical value, we got a local minimum. But again, I don't think anyone in the test would really do this analysis. They just assume that their critical value is a local minimum since they only found one of them and call that their answer up here. It's worth pointing out that I think you could solve this problem without any calculus at all, especially if you're kind of a good artist. I am certainly not a good artist, especially when I write on a tablet, but maybe even I can do it. We're interested in the curve y equals the square root of x plus 3. So maybe you're thinking that's the square root of x shifted 3 units to the left. I know that this curve goes through this point at negative 3, 0, either because I know that the curve y equals the square root of x goes through the origin, and this is shifted left 3 units, or because when I plug negative 3 into this equation, 0 comes out. So it must go through this point. Similar logic tells me it must go through the point negative 2, positive 1, and also through positive 1, positive 2. I know the graph of y equals the square root of x kind of has this shape right here. So I connect the dots as best I can, and I get a graph of this curve. It's not perfect, but I think it's close enough to get our answer. The origin is right here. The point negative 3, 0 is way the hell out here. Here's answer A. The point with an x-coordinate of negative 3/2 falls on my graph somewhere up here. The point with an x-coordinate of negative 1/2 falls on my graph up here. The point where the x-coordinate is 0 falls up here. And as we already talked about, this point isn't even on this graph. I guess if you're doing this analysis this way, it's a good idea to make sure that this is the y-coordinate for this x-coordinate, and this is the y-coordinate corresponding with this x-coordinate. But anyways, once you have this pictured, you might be able to just look at it and tell that C is closest to the origin. And you're like, nope, sure can't. Okay, that's fair. A property that's really useful, especially when we get to three-dimensional versions of this problem, is that at the point that's closest to the origin, the tangent line will be perpendicular to the line connecting that point and the origin. If I draw a line segment from the origin to C here, and then I draw the tangent line to this curve in purple at C, that's close enough to a straight line, it kind of looks like these guys are perpendicular. I can tell just by looking at it that A ain't closest to the origin, and I know that D is not closest to the origin because the tangent line at D is not horizontal, right? The graph of y equals the square root of x never gets completely flat. So the tangent line can't possibly be perpendicular to the line connecting the origin and point D, which is vertical. So just by plotting the points, maybe I could tell that my answer was either B or C. And if you draw these lines in light green, it looks a hell of a lot more perpendicular than if you draw a line connecting B to the origin, because the line perpendicular here would look something like this, and that's nowhere near the tangent line to the graph in purple at this point. The point that I'm trying to make is that because this graph here is differentiable, at the point on the graph closest to the origin, in other words, the answer to the question, the slope of the tangent line is perpendicular to the line segment connecting that point to the origin. As I write that down, I see it's kind of a mouthful, but maybe a picture will clear things up. Draw whatever curve you want. Sure, I don't know, something like that maybe. Call it f of x. Pick whatever the hell point you want. I don't know, maybe down here. Sure. We'll call that x, y. If I'm looking for the point on f of x closest to x, y, let's see, in this picture it'd be somewhere over here maybe. The tangent line to the curve at this point, drawn in dotted red here, has to be perpendicular to the line segment connecting this point to this point. You can memorize that or just kind of think about, what if it wasn't perpendicular? What if I thought that this point up here we're closest to this point? Well, because the tangent line at this point is not perpendicular, I can take this line in blue and kind of swing it around a little bit, move it until the tangent line becomes perpendicular. As I rotate it around, counterclockwise in this example, I see that there are shorter lines, like the line from here to here, that connect this point to this curve. Since this line in blue is shorter than this line in blue, this point can't possibly be the closest point on this curve to this point. And I can continue to play that game until the tangent line is perpendicular to this line, at which point I've minimized the distance. Technically, there could be more than one point where I have a perpendicular tangent line, right? Imagine if f of x, I don't know, continued like this maybe. Sure. There's some other point, I don't know, somewhere down here maybe, where the tangent line is perpendicular to the line connecting this point and this point. Really, all perpendicular tells me is that I have a critical value. So it could be a local minimum or a local maximum. In this case, it's a local minimum. In, I don't know, somewhere out here case, it looks like I have a local maximum. This point is closer to this point than any of its immediate neighbors. This point is further than this point than any of its immediate neighbors. But clearly this point is closer than this point or this point. So for my absolute minimum, this would be the one I'd care about. In this specific problem, we don't have any of those issues. There's only one point on this curve where we have this perpendicular idea. And better yet, it's multiple choice. So we can just label the different options and quickly verify that C is the only point where we have this perpendicular behavior. So either by using calculus, minimizing the distance function, or better yet, minimizing the distance squared function, or by sketching a picture and just looking at it, or better yet, sketching a picture and having this fact in your back pocket that we're looking for this perpendicular behavior that I described, you can come up with this answer C.